Uh,
Okay, I can see your screen now.
okay, so thank you for that. So good day to everyone. So allow me to discuss to you our topic entitled Machine Learning for Seismic Vulnerability Assessment, a review, authored by yours truly, Jeremy C. Jimenez and Orlene G. De la Cruz. So today's presentation is organized as follows. First, I'll be introducing to you our topic. Then, the materials and methods used for this review. Third, discuss the underlying topics for the review. Fourth is we identified the research gaps from the articles reviewed from this study. And lastly, the conclusion of this review. To start with, so Cao et al. Acknowledged that earthquakes are one of the nature's most devastating natural disasters, which causes immense economic and societal upheaval. When an earthquake strikes, buildings and other structures are no exception. By the year of 2008, Wenchuan, China experienced a massive earthquake with a magnitude of 8.0 that destroyed over 5 million homes and 69,000 people. The impact of the said earthquake can be seen from the image of can be seen in the image on your left. In July of 2022, here at the Philippines, the northern western part of Luzon has experienced a massive 7.0 magnitude earthquake. The aftershock effects of this earthquake can be seen from the image on your right. As we can see from the following photos, natural disasters like earthquake, tsunamis, and many more can never be avoided, but we can mitigate the damage they inflict. If one can have the ability to predict the potential damage caused by an earthquake, it will be possible to save the lives of thousands of people by averting the collapse of those buildings. So then machine learning is introduced. Machine learning has been widely used in the field of earthquake engineering. With the use of machine learning-based computation for seismic vulnerability assessment, there has been a reduction to computational costs compared to the traditional methods. The figure on your right by Kazemi et al. Shows the analytical procedures used for machine learning-based seismic risk assessment of reinforced concrete buildings. There has also been a wide usage of probabilistic seismic demand analysis, or the PSDA, to quantify the structure's behavior during the seismic loading conditions. So in this study, the researchers looked deeper in some of the research papers that shows a substantial benefit to using ML-based approaches instead of the conventional models. Challenges has also been identified. And by the end of this study, the researchers point out what needs to be done to verify the quality of ML-based seismic vulnerability assessment. Now for the materials and the methods. The researchers conducted a four-phase review process to explore the application of machine learning in the analysis of seismic vulnerability assessment. The Scopus database was used to search for peer-reviewed articles. The search was carried out using the following search terms: machine learning and seismic fragility assessment. There were 184 relevant papers identified through the database searching. And during the screening, exclusion criteria were applied to the identified papers. One paper was identified not within the year range of 2017 to 2023, and 4 of those papers were not in English or without English translation. So therefore, we have 179 papers undergone screening by title, by abstract, by introduction, and by conclusion. And 107 of those were excluded due to the fact that they are not related to the research question, and some of the full texts are not obtained. After the thorough screening process, the researchers acknowledge that 72 out of the 184 papers will be included in this study. So after identifying the 72 articles out of those 184, the 72 articles were imported and processed using the MATLAB's text analytics toolbox to create a word cloud visualization. So latent direct allocation, or LDA, was used to determine the degree of similarity between source files and how each document is distributed across the topics. So the figure on your right is the output of the MATLAB's text analytics toolbox, which shows the most commonly used terms. From those 72 papers, here are the terms: analysis, fragility, seismic, model, and bridge. MATLAB's text analytics toolbox also provides word cloud of topics presented in your screen, which are then used to interpret the specific topics for discussion. So topic 1 contained the following words: structural, seismic, base, approach, and result. So the topic was interpreted as the method of analyzing the seismic behavior of a structure. Topic 2 includes the words performance, bridge, model, fragility, and propose. So the topic interprets as the application of ML-based modeling in assessing the performance of the structures. Topic 3 includes design, structure, building, seismic, and earthquake. The topic discusses the design process of seismic-induced structures. And lastly, for the topic 4, we have concrete, analysis, seismic, study, and system. So the topic discussed was the development of seismic performance analysis of concrete structures. So for the first topic, we have here an overview of the probabilistic seismic demand analysis. So probabilistic seismic demand analysis, or PSDA, is a widely used or widely employed technique in earthquake engineering. It is used to assess the structure's seismic response behavior. This methodological approach enables engineers to understand the structure under seismic loading conditions. By incorporating this probabilistic approach, PSDA facilitates the evaluation of the potential demands imposed on the structures during the seismic events, thus enabling the engineers to make informed decisions in the design and risk assessment. So PSDA is an essential issue for the risk assessment of various structures. It is also an important step in the performance-based earthquake engineering, or PBEE, design framework. So in recent years, researchers have continuously worked to enhance the demand models and integrate machine learning-based methodologies into the PSDA framework. These efforts aim to improve seismic assessments, accuracy, and reliability, ultimately enhancing structure safety and resilience in seismic-prone regions. So for the next topic, we have here the outcomes measured in probabilistic seismic demand analysis. So the probabilistic seismic demand analysis encompasses various outcomes that are measured. In this table, the researchers identify the specific outcomes measured through the review of the included papers. So for the main category, we have here the column for the main category and the column for the specific outcomes. So first, we have the category of prediction. The outcomes measured here is the accuracy of prediction models and the prediction uncertainty. Next category is the costs and losses. The outcomes measured are the costs and the economic losses. So next category is the environmental impact. The outcomes measured, the embodied carbon emission, and the environmental impact. Next, we have here the engineering. Outcomes measured, engineering demand parameter, and failure modes. Next category is life cycle. Outcomes measured is the life cycle seismic analysis. We have also here the category for the intensity, which has the specific outcome of optimal intensity measures. Next category is damage. Outcomes measured is the probabilistic damage assessment and the seismic performance. And lastly, we have here the risk category. The outcomes measured is the seismic risk probabilities and the seismic vulnerability of the structures. So machine learning is a prominent area of research that focuses on the endowing of computers with the capacity to learn autonomously without explicit programming. So this field has gained considerable attention due to its potential to revolutionize various domains by enabling machines to acquire knowledge and improve their performance through experience. So machine learning algorithms can analyze vast amounts of data, identify patterns, and make accurate predictions. And many algorithms fall into distinct categories of machine learning. One is the supervised learning. The another is the unsupervised learning. And lastly is the reinforcement learning. So these algorithms serves as the fundamental framework for understanding and classifying the diverse array of algorithms within the field. Demand models plays an important role in the comprehensive evaluation of structures through the performance-based assessment. And machine learning has then been utilized to derive the seismic fragility curve parameters. So in this chart, it shows the widely used machine learning techniques in PSDA applications. As we can see that neural networks is the most common. Okay, neural networks are the most common choice of algorithms in PSDA. Next to which is the Bayesian learning, the random forest, and the support vector machine. So for the next topic, we have here the development of probabilistic seismic performance modeling. So in utilizing the machine learning techniques, it holds promise to enhance the probabilistic seismic modeling efficacy. Machine learning has also become integral to various applications, such as the identification of the seismic fragility curve, in which this seismic fragility curve is also a significant outcome of the PSDA. And according to Vora et al., the most crucial part of applying machine learning in predictive modeling is choosing which algorithms to use. And the effective use of ML algorithms was observed depending on the chosen methodology. So with that being said, the researchers had then identified the research gaps presented in those studies. The following are the established challenges in machine learning-based PSDA. Number one is the limited access to data. Number two is the limited practical application. Number three is the quality of resulting models. And lastly, we have the versatility of algorithms. And the effectiveness of an ML algorithm is affected by the features used, the size of the data set, and the balance between training and testing data. Then several research studies found that it is challenging to interpret machine learning-based models, raising concerns about the quality of the resulting models. Further research is needed to utilize machine learning in seismic vulnerability assessment fully. In conclusion, machine learning algorithms is the cause of robust computation of the PSDA and rapidly assess the response of the structures in conjunction with the earthquake. However, several gaps or several challenges were also presented. So here are some of the challenges, or here are the challenges met in using the machine learning based PSDA. So in machine learning PSDA, there's a limited research tackles the wide usage of ML or machine learning in earthquake engineering. We have also the limited data sets pose a significant challenge in the application of machine learning, limited practical applications of machine learning in PSDA. So one of the challenge of machine learning based PSDA is that some of the machine learning models are more or less black boxes due to the training process. And also, it is only limited to a single learning algorithms. So therefore, further research is needed to investigate the usefulness of machine learning in PSDA or probabilistic seismic demand analysis thoroughly. So our paper makes a valuable contribution to the study of probabilistic computation in civil and structural engineering. And also, these are the references used during the literature review of PSDA. So thank you so much.
Okay, thank you. Thank you for your excellent presentation. Does anyone have any question? Okay, no one. Okay, thanks again for your excellent presentation.
Thank you.
Thank you. Okay, now let's welcome our next